This is a Nobel Prize-winning quantum physics experiment that I've turned into a musical instrument. Here's what it sounds like. The original experiment essentially showed that electron orbitals are quantum states, not electrons literally orbiting a nucleus. Okay, so the electrons aren't orbiting, then what are they doing? The answer to that question, if you don't already know, is so bizarre it will completely melt your concept of reality, which is a big claim, but you tell me. It all starts to fall apart when you understand what I mean by a quantum state. So we're used to reality being essentially a bunch of objects located in different places. Like this object's over here, and that object is over there, and this electron is right here. But according to quantum, that's not how the world works. The electron isn't here, and actually it doesn't really exist as a physical object at all, like you might imagine a little yellow ball. It actually exists as a cloud of all the possible places it could be without actually being in any of those places. It's more like when you imagine your future and there's all these different possibilities, but none of them exist yet. Those thoughts about your future, where all these things are possible but nothing is concrete yet, is kind of like how the electron exists, like a cloud of possibilities. But it doesn't exist as any one of those possibilities in particular. When you see these figures of electron orbitals, you're looking at probability clouds of where the electron could be located. But just to be clear, it's not like we just don't know where it is. It literally exists as this cloud of possibilities. If the electron was actually orbiting around the nucleus, there's no physical reason why it couldn't orbit really close or really far or any distance in between. And if it can orbit at any radius, then there should be a continuous spectrum of orbital energies. But that turns out not to be the case. And that's what the Franck-Hertz experiment shows. It shows that electrons can exist at a couple different energy levels, but not just any energy level. That's actually what makes it quantum. Quantum just means it's either this or that, and there's no in-between. It's quantized. So in this case, the electron either has this energy level or this energy level, and there's no in-between. Actually, that has some mind-bending implications too, because it turns out our position is also quantized, which means in order for a particle to move from one spot to another spot, it essentially has to teleport. But actually, most of the time, the particle doesn't exist in any physical place at all, unless you look at it, and then it does physically exist in a particular place. Sorry, I'm getting carried away. Let's get back to the Franck-Hertz experiment and how to make it a musical instrument. So the goal is to show how electron orbitals are quantized. How do we do that? It's kind of a roundabout way of proving it. So first I'll explain how the experiment works, and then I'll explain why it means the orbitals are quantized. The key to this experiment is in this glass tube with all these sciencey looking metal pieces inside. Here's a diagram of that tube so we can see more easily what's going on. It's a vacuum tube, which just means it's a glass tube with all the air sucked out. But this tube is a little bit different because we add a little gas back in. The original experiment used mercury, but I use neon because I don't want to accidentally poison myself. The electronics in the tube are set up to make the electrons fly from one end on the left to the other end. This part is a filament like what you would see in a light bulb, and pumping electric current through it not only makes it give off light, but it also makes it spray electrons everywhere. Then once the electrons are loose, we encourage them to fly over to the other end of the tube with this mesh grid that we charge to 6.5 volts. The electrons are negative, so they are attracted to this positively charged mesh. And once they reach the mesh, a lot of them hit it and go away, but a lot of them fly through the holes and continue in this direction. So now that they're flying in the right direction, we want to control how much energy they have. To do that, we charge up this mesh grid to somewhere between 0 and 80 volts. If we charge it to 0 volts, they won't build up a lot of speed, but if we charge it to 80 volts, they'll fly through the mesh, some will hit the mesh, but a lot will make it to this part. If they hit this metal plate, they'll be registered as a current, which is our output signal. This plate is not as high voltage as the mesh that they just passed through, so If they aren't going fast enough, they'll actually slow down and stop and go backward and land on that mesh. If they land there, I won't measure any current because I only measure the electrons that hit this plate. So the electrons need enough momentum to fly through this grid and hit this plate, even though they're being pulled backward in this region. If this tube didn't have any neon in it, here's how it would work. I would start at 0 volts and slowly increase the voltage on this mesh, and what I would measure is, as I turn up the voltage, the number of electrons that hit this backplate would also go up. So the graph would look like this: voltage on the x-axis and the output current on the y-axis. See, as the voltage goes up, the current also goes up. But if I add a little bit of neon in, then the graph turns into this. These waves are telling us that the electron orbitals of neon are quantized. What's happening is, as I raise the voltage, the current starts to go up, but if I raise it high enough, some of the electrons start to have enough energy to knock the electron within neon to the next orbital. If the electron that's flying through the tube doesn't have enough energy, it just bounces off neon, and the speed doesn't change at all. There's a very specific amount of energy between neon's energy levels because the energy levels are quantized. So the electron flying through the tube needs at least that amount of energy to excite the neon atoms to the next energy level. Once that happens, now the electron is going slower because it donated a lot of its energy to neon. That means when it comes time for this electron to enter this region, it's not going to have enough energy to make it to the back plate. It's going to turn around and hit the mesh. The more I crank up the voltage, the more electrons reach this energy threshold that they need to donate their energy to neon and push its electron to the next energy state. So now the number of electrons that have enough energy to make it to the back panel starts decreasing. And as a side note, once neon is excited to a higher energy state, it immediately reverts back to its original state and releases a photon. That's actually where the neon color from neon signs comes from, and that's the neon color that you see in this experiment too. If I continue to crank up the voltage, now some electrons have enough energy to donate to neon and still have enough momentum left over to make it past this region that's pulling them back. So we start seeing the current rise again. The current will continue to rise until we start to see electrons that have enough energy to donate to 2 neon atoms, but not enough energy to make it past that region that pulls them back. You can actually see the bands of light where the electrons gain enough speed and energy to interact with neon and then have to regain all that speed to interact with neon again. But if electron orbitals were not quantized, we'd probably see the current rise steadily as we increase the voltage, not this wavy pattern. If it weren't for quantum, there's no reason why this wavy pattern would show up. We're finally ready to turn this thing into a musical instrument. Maybe some of you have noticed that this is sounding a lot like a tube amplifier, and if so, congrats, because that's exactly how I treat it. For those who aren't familiar with tube amplifiers, I'll explain. First, I set what's called a bias voltage on this mesh grid, and I let the signal from my guitar either raise or lower the voltage. In a regular tube amp, the vacuum tube doesn't have any neon or any other gas in it, so the voltage current graph looks like this. Notice it's a straight line, which means you can turn a small swing in voltage from your guitar into a large current swing, which comes out of your speakers and is really loud. But the key is the output should be the same signal as your input, just louder. That's what it means to have a linear response. That is, unless you turn up your tube too much and you push your signal into this region of the graph, and actually that's where tube distortion comes from. Anyway, my voltage current graph is completely whack because of quantum physics. If I don't turn it up too loud, it actually sounds like a normal guitar because this region is pretty close to linear. But if I keep turning it up, now for every wave of the guitar string, the quantum physics is adding these small waves on top. Those smaller waves on top are called overtones, and that's what gives the instrument its signature sound. I'm thinking about making a video about how I built it, and maybe a video about how I designed the circuit to make it work. It was actually a pretty painful process. I had to make something called a picoammeter, which essentially measures super tiny currents, because the currents from this tube are actually super tiny. It was measuring currents so small that it could detect when I walked into the room. I had to order these Soviet-era vacuum-sealed resistors, which I had to put on gloves to handle. It was a whole thing. Anyway, let me know if that sounds interesting or if you're just here for the high-level fun stuff. You can find the sounds of this instrument and a whole bunch of other cool instruments on Operville, which is my new album. And to end the video, here's a song from Operville where the first sound you'll hear is me playing a C-board, which is like a gel keyboard, through the Franck-Hertz experiment.